Okay, I'll get started. So this last lecture is going to be discussing some data analysis techniques. So it's going to give you a bit of an overview of the sorts of methods we use to extract meaning from gravitational wave data. Now, if you're talking about data analysis, there are two things typically you might want to do. You might want to say, is there a source in the data? And you then have decided that there is. You want to say something about the properties of that source. So that is the issue of detection. Can we say that there is a binary black hole signal in the data? And then the issue of parameter estimation, given that there is a signal, what are the masses and other properties of the system? So I'll spend the first part of the lecture talking about techniques for searching for signals and deciding whether there's sources in the data or not. And then the second half will be on the parameter estimation side. Okay, so we've touched on one of the primary tools for searching for signals already, and that's this issue of match filtering. If you remember in lecture 1, we talked about this linear optimal filter, which is the one that maximizes the signal-to-noise ratio in a filtered time stream. And this is a filter that in the Fourier domain is proportional to the signal you're looking for, weighted by the noise in spectral density in your detector. Okay, so the argument we did to derive this optimal filter, we were assuming we knew exactly what the signal was that we were looking for. In practice, we don't know that. We may have a particular category of source that we're interested in, for which we can model, but that source will typically depend on some parameters, the masses of the black holes, the spins, and so on. So we won't have a single template, but we'll need to look at many templates. So searching for one of many signals, it's not optimal to take maximum template bank, but it is approximately optimal and it's near enough. And so that's what we tend to do. We construct a template bank of possible waveforms representing everything that might be in the data in a particular source category. We construct this optimal filter for each one, and we take the overlaps of all of these templates with the data and see if any of them have a particularly high overlap. So you have some noisy data, you have templates which represent chirps, offset in time. You construct overlaps of these chirps, in this case, sensitive at different times, and you find a significant signal when your template lines up with something that's in the data. Okay, so that's the basic principle. In practice, there are a few complications, which I'll talk about over the next few minutes. Now, one thing to remember is that this process of match filtering is closely related to another statistical concept, that of likelihood. If you remember, in the first lecture, we talked about this notion of stationary processes, for which the noise properties are given by at different frequencies are independent, and their variances are characterized by this spectral density. If we assume that the noise is Gaussian, then from this relationship you can write a probability distribution for the noise in the data, and so the probability of that the noise is a particular value is just proportional to the exponential of the overlap of the noise with itself, using this definition of overlap that I also introduced in the first lecture. Okay. So if we have a data set that it has noise and signal, then the likelihood that the signal in the data has some particular parameters is just the probability that the noise realization is equal to S minus H for that particular choice of parameters. And so you can see that the maximum likelihood estimate of your signal parameters coincides with the template that has the maximum match in terms of this SNR definition with the data. So you can think about match filtering as being a maximum likelihood type search where you're considering a finite set of possible signal templates. Okay, so motivated by that, you can introduce something called the linear signal approximation. You can say, well, let's suppose that my data actually has a signal in it that has parameters lambda naught. You don't know what lambda naught is, you're trying to estimate it. And so if we assume that the signal is quite loud, we expect to get close to lambda naught, but we'll be thrown off a bit by noise. And so we can assume that our template is close to being the true template, but with some correction due to errors we made in the parameters. So if you plug this model into your likelihood, you can basically expand it, and you find that this likelihood looks like a Gaussian. It's centered at a non-zero value of parameter error that depends on the particular noise realization. The expected error is zero, because the noise has a zero mean. But for any particular data set, you'll expect to be slightly off the true parameters, but you'll get a likelihood that has a width that is determined by something called the Fisher information matrix, which is basically the overlap of waveform constructed by taking the overlap of derivatives of the waveform with respect to your various parameters. Okay, so you'll see a lot of papers in which the Fisher information matrix is calculated. This is how it's defined. The reason that it's relevant is because it characterizes this shape of the likelihood, and it gives you an estimate of how much you are uncertain in particular parameter values. So from this Gaussian approximation, you can see that if you take the inverse of the Fisher matrix, then the diagonal elements of that tell you something about how much you typically expect to be moved away from the true parameters as a result of noise fluctuations in your detector. So it's a measure of the precision you would expect, in theory, on measurement of a particular parameter. Okay, so this is widely used to assess how well we might measure things, and all of those numbers I gave in the previous lecture on how well we can measure masses and spins and eccentricities using supermassive black holes and emeries and so on, they were based on calculating this quantity, the Fisher matrix. Oops. One more second. Okay, so as I said, the Fisher matrix gives you an estimate of how precisely you can measure parameters. It also tells you how close you need to place templates in your template bank if you want to be sure of seeing all the signals. So this Fisher matrix is the measure of how much you get shoved around by noise fluctuations. It also tells you how rapidly your templates become orthogonal to one another as you move in parameter space. And so if you want to construct a template bank, we want to be sure that we're going to see everything. Now, unless you have templates everywhere, you can't be completely sure, but what you do is specify something called a minimal match. You say that the worst possible case, we want the overlap of the true signal with one of the templates in our bank to be at least 1 minus this minimal match. So, we might have 3% as, so I think this should be minimal mismatch with this definition. If it's minimal match, then you don't need 1 minus. Okay. So typically we would say we want the overlap of our template bank with every possible source to be at least 97%, and that tells you how close together you have to place templates to be sure that any randomly chosen true signal is not too far from one of those templates that you don't see it. Okay. So this notion of using the Fisher matrix as a metric on your parameter space allows you to place templates in a sensible way, because it tells you where you need, it tells you which directions in parameter space you're degenerate, and so you can use fewer templates if you place templates along the eigendirections of the Fisher matrix. That works well in low numbers of dimensions, 2 or 3, but for most reasonable, most realistic scenarios you might encounter with LIGO, you're talking about much higher numbers of dimensions. And so using the Fisher matrix to define a metric gets very complicated, and so what you'll tend to find these days is that people are using stochastic banks So you essentially randomly put down templates until every additional template you choose has overlap of at least your minimal match with at least one of the templates in the bank. Okay, so you just do it randomly, and we found so people have found that studying stochastic banks, you don't end up with too much overcoverage. So you can construct the stochastic bank, compare it to your optimal bank based on the Fisher matrix criterion, and you maybe have a factor of a few tens of % too many templates, but it's not terrible that it ruins your computational efficiency. So template bank approaches are what is currently used in LIGO and what we may use for certain searches in LISA. A lot of the work that's been done on LISA data analysis in the context of the mock LISA data challenges that happened about 5 to 10 years ago focused on stochastic searches. So these are slightly different. You don't have a fixed template bank, but you effectively generate the bank on the fly by doing essentially the same thing you do for parameter estimation, like Markov chain and Monte Carlo, which I'll talk about in the second half of the lecture. You can do this for searches as well. You just, based on where you currently are, you look at nearby points until you start to find the signal. And so then you generate many fewer templates for any single search than you would need if you constructed a template bank in advance. Okay, so that's the basic principle. We have a bunch of templates, however they're constructed, and we take overlaps with the data, and then we look to see if any of the templates have a particularly high overlap. But that's not all we need to do, because you can get quite a high overlap with a template without actually matching that template very well. LIGO, so everything I've talked about has made this assumption of stationary Gaussian noise, but LIGO is non-stationary. It has glitches that happen from time to time. These glitches can have quite high SNR. If you have a signal that has lots of SNR, then it will give you quite a lot of SNR in a template, even if it doesn't match that template very well. So it'll match a bit of the signal, that gives you quite a lot of SNR, and so it will ring off this template, and you might think that you have a real trigger. And so what we have to do, as well as just looking at the pure signal-to-noise ratio in the template, is check that the way in which that SNR is distributed is consistent with what we would expect for a signal of that type. So in particular, if you look in the frequency domain, again in this Gaussian approximation, if you subtract your template from the data, then this should just be something that's a Gaussian distributed random variable. It's your noise, and so if you square that and divide by its variance, it should be a standard 1 degree chi-squared variable. Okay? And so if you look at your frequency, a bunch of frequency bins, and you sum up this residual square divided by the noise over all these frequency bins, you should get a chi-squared distributed variable. Okay. Now, if you have had a trigger due to something that's not actually a signal like what's in your template bank, but has very loud amplitude, and so it's a fake detection, this chi-squared is going to be large, because when you take off your best model in your bank, you still haven't taken out much of the power in the signal, so you get much larger values of these sk minus hk squared terms in the denominator, and so your chi-squared consistency check tends to be big. And so based on this, both of the LIGO pipelines that use template banks use something like this chi-squared to check consistency of their best template with the data. In the PyCBC pipeline, which I'll describe in a minute, they use something called effective signal-to-noise ratio, which basically divides the recovered signal-to-noise ratio by 1 plus something that depends on this chi-squared. So where this thing is big, so you're not taking out much of the signal power, you significantly reduce your effective SNR, and so then that indicates that it's not a real signal. And what's shown here is an example. This is from the LBC paper that described the pipelines at the time of GW 150914. You have chi-squared, so this chi-squared quantity on the vertical axis and SNR on the horizontal axis. This purple band here is a bunch of injections that were made, and the black things here are noise triggers. So there's a nice separation when you account for chi-squared and rho, which you don't get so much at individual values of SNR. So including this chi-squared does help you to separate true signals from noise triggers.
So the powers of 3 and 1/6, is that motivated by theory or is it empirical?
Yeah, that was a good question. As I was writing the slide, I was like, why did they choose that? The answer is I'm not completely sure. I think it was motivated practically rather than theoretically. So it appeared to be something that, so these dashed lines I think are contours of constant rho hat, and this sort of tracks this separation between signals and noise better than. Okay, so we've talked about template banks, we've talked about consistency checks. The other thing that these searches depend on is noise estimates. Okay? So we said that the match filter is the true signal divided by, so it's the Fourier domain signal divided by the noise. If you know what the noise is, then that's fine, you can construct these things, but in general, we may know roughly what the noise level should be, but we don't know it exactly. And so if you want to be more sure of your power spectral density, you should try and estimate it from the data. And so what happens in LIGO is that they might have a section of data, which will be typically a few seconds long, that has a trigger in it, and they then take data in the vicinity of the trigger in segments of equal lengths, and use these segments that are off the source to come up with some estimate of the PSD at each frequency. Okay. Now what I've written here is not how it's done in practice. This is just taking the mean of the squares of the noises. This is an unbiased estimator, but it is more vulnerable to fluctuations in the tails due to glitches and so on. And so in practice, the LIGO uses a median estimator rather than a mean estimator. But the principle is the same. You're looking at data without a source, but in the vicinity of the event in order to estimate the noise level. For LISA, we don't know how we're going to do this yet. We don't have off-source data for LISA because all LISA sources last significant fractions of the mission duration. And so this is an open question, how we estimate spectral densities for LISA. Most likely it will be based on coming up with some parameterized model of the noise that we then try and constrain using all the data. Okay, so those are the ingredients that go into a match filtering search. And what this whole procedure gives you in the end is a method for calculating a number from the data. Okay? This is what we call a statistic. It's a quantity that is a function of the data. It's, in this case, a complicated function. You're doing a PSD estimate. You're using that to construct your template bank, which is then used to do match filtering with the data. You take the template that has the highest effective chi-square, effective SNR once you've accounted for the waveform consistency checks, and so on. So it's a complicated procedure, but you end up with a single number that characterizes how likely it is that there is a source in the data or not. Okay? Now, if the noise was stationary and Gaussian, you can then work out what the distribution of that quantity should be. And so you can then set some threshold of false alarm probability such that it is very unlikely that a given trigger would have come from noise, and so it looks like it flows like this. In practice, LIGO does something slightly different, and that's because we don't want to make the assumption that the noise is stationary and Gaussian, and so we try having not only to estimate the PSD using data, we try and estimate the background in the search using data. And this procedure is based on things called time slice. You use the fact that you have two detectors to try and construct signal-free data sets. So the LIGO detectors are 4,000 kilometers apart or so in the US, and the light travel time between the two detectors is about 10 milliseconds. So if you take the data from one detector and the data from the other detector, and you shift the data from the second detector by at least 10 milliseconds, then you know that any triggers that are coincident between your two detectors must come from, by chance, they must come from noise. Okay? And so the way LIGO background is estimated, so we have these statistics which are in individual detectors, you combine them in some way over multiple detectors, and then you construct a background by creating these fake data sets in which every trigger has to be due to noise. Okay. This is a long process. It uses a lot of computation power. That's one of the reasons it took so long to do the 1509-14 analysis. There was 16 days of LIGO data available, but they had to simulate 200,000 years of LIGO data to be sure that 1509-14 was a 1 in 200,000 year event. Okay. So one final, I think, thing on this is to mention that there are cheaper ways to search for some parameters. Okay, we say we've got a template bank. That template bank covers our parameter space with a certain match. But there are types of parameters that you can search over a bit more cheaply. And the main ones are phases and times. Okay, so this is an illustrative example. The idea is that if we have, if our waveform template depends on a phase parameter, so it's something like cosine of 2 pi f naught t minus tc plus some phase, then from standard trig identities, you can write this as cos of 2 pi ft times cos of phi naught minus sine of 2 pi ft times sine of phi naught. And then basically you can analytically find the phi naught that would maximize your overlap if you know what the overlap of the cosine and sine quadratures are with the data. So if you take this template with phi naught equals 0 or phi naught equal minus pi by 2, take those overlaps of the data, square them and add them together, you've effectively maximized your overlap over possible values of phi naught. Okay? And so that means that rather than having to have 100 templates to cover the phi naught space, you just have 2, and you can still maximize over phi effectively. There's a similar, well, there's a slightly different trick you can do for time. This is based on Fourier transforms. If you take a Fourier transform with a time shift, you're just multiplying by a phase in the Fourier domain, e to the minus 2 pi I ft. And so you can see that the overlap of the data for some arbitrary tc is just the overlap for tc equals 0 times e to the minus 2 pi I ftc. So this is an inverse Fourier transform of this quantity. And you can do inverse Fourier transforms cheaply using fast Fourier transforms. And so a way to maximize over times in logarithmic, so in a way that scales like the log of the number of independent times rather than the number of independent times, is to use this Fourier transform trick. And so that's also used in LIGO. Okay, so those are the basic principles of match filtering. I'll say a few words about the LIGO pipelines and then move on to other types of search. So LIGO uses 2 different pipelines to match filtering, looking for compact binary coalescences. They operate on all of these principles I was just talking about. There are some subtle differences. The reason LIGO has 2 pipelines is to give great confidence in the results, because they are doing things slightly differently. If they came up with inconsistent results, that would indicate something funny is going on. So one of them is called PyCBC, the other one is called GST-LAO. PyCBC operates very much like I just described. There is a template bank, you get the compute this chi-squared fit, and from that the SNR. That gives you your ranking statistic, and then you compute the background using Thomas models. GST-LAO has a few subtle differences. It uses a template bank, but it does a decomposition of them, a singular value decomposition, so it essentially finds a lower dimensional representation of those templates, and it uses overlaps of those things with the data to define a likelihood. The likelihood is evaluated for a signal model and a noise model, and you can get a likelihood ratio, and that's the detection statistic. They use a waveform consistency test as well, but it's not a modification to their ranking statistic. It is a separate test that the signal-to-noise ratio accumulates in the right way. So we know if you have a particular template that the BSNR should continuously accumulate as you add more data. If it doesn't do that, it implies you've matched a bit of the signal on that whole thing. So that's another way to do this consistency check. And so GST-LAO does it that way. But again, when it comes to assessing background, it's using this time-side approach of taking data from the two different detectors and offsetting it. Yeah, so this is what this procedure gives you in the end. This is a plot from the one of the papers published at the time of the announcement of GW 150914. What is shown here, this is the output of the GST-LAO pipeline, so it's a log likelihood is their ranking statistic here. What you have on here is a black line and a blue line and then some orange squares. Okay, so the black line here is this estimate of the background. What they've done is construct a large number of other data sets by offsetting data from one detector with data from the other detector, and they look at then the distribution of their ranking statistic, which is this log likelihood, over that large number of data sets. And that gives them this distribution, which is shown in the black line. Okay, now, if you're doing that and you do have a signal in your data, then that signal is present in those two data sets that you're offsetting against one another. So there is a chance that that signal lines up with some noise in the other detector. And so this black line, some of this tail is actually due to GW 150914 in one detector lining up with noise in the other. And this blue is what you get in the background if you basically exclude 150914 from the triggers. Okay? Even in over itself background, the probability that this is noise is very small. It's a 5 sigma detection, even if you don't ignore it when calculating the background, and it's more like 10 sigma if you include it. So the results for PyCBC look quite similar. The background distribution is not as smooth, but the significance is quite comparable, and the interpretation of the various curves here is exactly the same. This is the output of PyCBC, where the detection statistic is this effective SNR rather than a likelihood ratio. Okay, so that's what's done for LIGO. What will be done for LISA is not yet decided. But people have been playing around with it for a while. There were a sequence of mock LISA data challenges back at around 2008 to 2011. And match filtering was widely used for LISA searches as well. The complexity for LISA is that we have lots of sources that are radiating all of the time. Okay, so we've got thousands of binaries, compact binaries in the galaxy, a few to a few tens of supermassive black holes per year, some of which have SNRs as much as 1,000, and MREs that could be anywhere between a few and a few thousand, which last for the entire duration of the mission. And so when you put these all together, you have this sort of cocktail party problem that you have lots of sources that are overlapping one another. Okay? And so This notion of using a template bank for LISA doesn't work so well because you can bring in a template bank that allows not only for one type of signal but all types of signal simultaneously. So it becomes a bit more complicated. But the principles of what we will do, which is use models of signals to dig them out of data and check for consistency with SNR buildup and so on, these are certainly going to be the same for LISA as they are for LIGO. Okay, so a couple of examples from these mock data challenges. This is for galactic binaries. There's in the center of each of these panels is the true parameters, and these are yeah. So there are lots of binaries in the data set. And the round circles here are estimated parameters that were recovered by different groups, where the pluses are the two true parameters of the binary. You see that they don't quite line up in all cases. Some of them line up quite well, some of them don't. This is because of noise in the detector. It's moving around, but it's not moving around by an amount that's inconsistent with the predictions of the Fisher matrix. For supermassive black holes, there's a lot of numbers here. You don't need to worry too much about them. The thing to look at is these last two columns, which are the fitting factors. That's how much of the signal-noise ratio of the true signal was recovered by the best template, and these are pretty close to 1. So we were able to recover these signals pretty well in most cases, and we were also able to do it for MREs as well. Okay, so we have demonstrated in principle we can do match filtering for LISA, although there are still lots of questions that need to be answered. In particular, we have not done this for a realistic data set containing all sources in their right numbers. Okay, so that's match filtering. You can only do match filtering if you know what you're looking for. And we can't be sure that we're clever enough to predict everything we're going to see. And so there is a need to do things that don't make assumptions about waveforms as well. So we want to do unmodeled searches too. These used to be called excess power searches, because that's the primary metric you're using. But there are a number of flavors of this, although they're all quite similar. Okay. So how do you do an unmodeled search? Well, one thing you can do if you don't have a model for your signal is use the fact you have multiple detectors. So we were saying that the background for these match filtering searches is estimated by taking time slides and looking how often you get coincidences. The same principle, if you don't do time slides, any sort of excess event in a detector that you see at the same time, or at least within 10 milliseconds in your various detectors, could be plausibly a real signal. So you can, using multiple detectors, you can do a coincidence analysis. The other thing you can do is look for sort of structure in the time frequency properties of your data. Okay, so the basic idea here is that you take your long data set, you divide it up into chunks in time. For each one of those chunks in time, you do a Fourier transform, so you get the frequency content, and then you plot these on a grid with time going one direction and frequency going on the other, and then you look for patterns in that data, and you look for these that are things that are consistent, coincident between instruments. Oops. That's interesting. I'm not sure why this slide appeared there as well, so let's ignore it for the moment, because I'll delete it before I give the slides to Barry. Okay, so there are 4 different pipelines that are used by LIGO. One of them is called OLIB, which I'm not going to talk about. They all work on similar principles. The first one is coherent wave burst, and there's also something called X pipeline. They work along the lines I just mentioned. They construct these spectrograms at different resolutions, so using different intervals in time and hence in frequency. And then they identify pixels that are bright, and then they look for clusters of pixels, and then having identified clusters of pixels, they mark these as events, and then they try and construct properties of those events that they then use to distinguish noise from signal. So an example from coherent wave burst is they, for a given cluster of pixels, they construct its coherent energy versus its residual noise energy, and the ratio of these two is then a statistic that you can use to characterize whether this thing is more likely to be signal or noise. So you're doing something like adding up the power in your cluster and comparing it to the average power in the whole spectrogram, and if that number is large, then it's likely to be a significant event, and if it's small, it's more likely to be noise. Now, these bursts, so coherent wave burst has not detected anything in LIGO data that was not also seen by an in-spiral search. So the only events LIGO has confidently detected so far are these black hole and binary mergers and the neutral star binary mergers. But these unmodeled searches are sensitive enough that they've seen many of the binary black holes. So GW150914 was detected first by coherent wave burst. And that's because coherent wave burst was running online in real time, and so it triggered on this event fast. And that's because this is a very bright binary, it's actually easy to see in the spectrogram. It helps that it's very massive, so your power is quite concentrated in a range of frequency and time, and so it was very easy for these burst searches to find it. The second binary black hole that Lisa saw, the Boxing Day event, 151226, that wasn't seen by the burst searches. Now it has almost as much significance as 150914 in the in-spiral searches, but it has much lower mass. That means it's a much longer signal, and so that power is spread out much more in the time frequency spectrogram. And that means that you can't see it so well in a burst search, which is looking for a concentrated blob in your spectrogram. Okay, so I mentioned earlier, we didn't say anything much about it. It's coherent wave burst. There's also something called X pipeline. It's essentially does the same thing as coherent wave burst. Some subtle differences in the same way that pi CBC and GST Lao are quite similar, but with a few differences. But it's essentially the same procedure. X pipeline whitens the data, FFTs it at multiple resolutions, so you get these spectrograms. It then does some threshold on the pixel power to identify what it calls black pixels, things that are bright, and then it starts clustering these and then characterizing them with various quantities like the start time, the time of peak energy, the length of the track, the start frequency, the frequency at the peak energy emission, bandwidth, and so on. So from all of these quantities that X pipeline extracts, it then does clustering on them in between different detectors, and then tries to separate background from noise by taking clever cuts on derived quantities. So one thing that X pipeline produces is an estimate of the coherent energy versus the incoherent energy. It must be the other way around, incoherent versus coherent. And you then do injections and time slides, and you get a plot that looks like this. All of these things at the bottom are noise events. All these things at the top are real gravitational wave events. And so you can see that if you put a curve through this that looks like that, you can distinguish your signals from your noise. Okay? But as I said, the process is quite similar. You're throwing away phase information by constructing your spectrogram. You're looking for bright patches in your spectrogram that line up between different detectors, and that allows you to then identify potential candidate events. Yep.
What does it mean, whiten the data?
Right, so whiten the data means basically get rid of this nasty spectral density term. Right? So you're essentially, in the time domain, you divide your data by the square root of the spectral density, and that means that the noise is now white So of this, after doing this transformation, you're taking your spectral density was SH, but you now, so your spectral density of n divided by root SH is now 1 at all frequencies. And so that means that in the absence of signals or glitches, this looks uniformly blue. Okay? If you don't do whitening, then because the detector has more noise at lower frequencies, you'll have red patches down here and red patches up here, and so then it's much harder to do this contrast because you'll need to be looking for things that are bright relative to similar frequencies rather than just bright in some blue results. So this whitening makes the spectrogram flat and then does the analysis just to make it easier to set thresholds and things. Okay, so the final unmodeled search pipeline that's being used for LIGO is something called BaseWave. It takes a slightly different approach. It's a more parameterized approach than the others. The others are just looking at spectrograms and then constructing some quantities based on the pixels. BaseWave is not throwing away the phase information in the same way. It's trying to basically model the output of the detector as a superposition of different components, some of which represent noise and some of which represent signal. Okay, so it models the smooth components of this power spectral density, which is the Gaussian bit of the noise. It represents that as a cubic spline, so it has a small number of points along the spline, but it has enough flexibility to soak up variations in the Gaussian noise that might take place. It models lines that we see in the spectrum. There are points where the suspensions vibrate at a particular frequency, or you have electrical noise at multiples of 50 hertz, which is the AC frequency in the US. You model those using Lorentzians. These are basically things that are a bit like delta functions, that can be tuned to be close to being delta functions. And then the rest of the noise is modeled using wavelets. Okay? Now a wavelet is, so it's a bit like doing a spectrogram. So a spectrogram, you take chunks of data in time and then you represent them as a bunch of discrete frequencies. A wavelet is similar. It's basically something that will be concentrated in time and frequency, and so it represents a particular component in your spectrogram. The difference between BaseWave and the others is that you selectively add wavelets rather than doing the decomposition into time and frequency over the entire range of possible times and frequencies. Now the choice that BaseWave uses is something called a Morley-Gabor. I think this was a spell checking correction. It should be Morlet-Gabor basis. These are basically sine Gaussians, so you have something that is a sinusoid multiplied by an e to the minus x squared type term. So it's something that is concentrated at a particular frequency in a particular time. The way the wavelets are used by BaseWave is by having some that are coherent between detectors and others that are incoherent between detectors. So it models the data as in a given detector as a sum of these wavelets just for that detector and a sum of other wavelets that are then the same between different detectors. And those coherent components are supposed to represent possible signals, and those incoherent bits that are different from detector to detector, they represent transients in noise transients in the individual instruments. So this is the overall picture. You have data coming out of your different detectors. It has a noise component. This is the bit that's modeled as this smooth PSD plus Lorentzians. Then you have the wavelet components, some of which are different between detectors, which are to model glitches, and some of which are consistent between detectors, and they represent signals. Okay, now BaseWave is called BaseWave because the way in which it decides whether it should add extra wavelets in is using Bayesian techniques, which I'll talk about a bit more in the second half of the lecture. But the idea is it iteratively adds wavelets to this model until the gain you get in fit from adding another wavelet is not enough to warrant the extra degrees of freedom you're including by having more parameters in your model. Now, Bayes-Wave works very well, and you may have seen, so there's a plot similar to this, not exactly this one, in the GW 150914 detection paper. You can see that there is this pale blue band here, which is that's basically the sum of all of the coherent wavelets that Bayes-Wave identified. So this is the bit that Bayes-Wave thinks is common between the two detectors, as projected in H1 and L1. And you see, it looks pretty much like the signals you see for 150914. And indeed, this Bayes-Wave search did recover a signal that looked very much like the simulations done with numerical relativity for the parameters that were estimated for 150914. So it's a very powerful technique, and if we can adapt it to use for LISA, that would be great. But there are complications for LISA because we don't have two independent detectors, or at least not really two independent detectors. So we have to more development is required there as well. Okay, so there have been a few attempts to use these kinds of methods for LISA in the context of these mock LISA data challenges. It was only really used for emeries by me and a few other people. We just explored whether the same sort of ideas of looking at a time frequency spectrogram and trying to find bright pixels or clusters of bright pixels and so on was able to recover emeries. Okay, now it did fine. We thought we could see emeries using these time frequency methods out to about 2 gigaparsecs, which is not too bad. It's a redshift of roughly a half. But we only ever succeeded in doing this when there was a single emery in the data. So what we find for emeries, because of the eccentricity and the inclination of the orbit, which leads to the orbital plane precession, you tend to get multiple tracks. So rather than a nice single chirp, as you get for an in-spiraling black hole, for emeries you get a sequence of chirping tracks, and so it's a bit more difficult because the power is spread out, and so you need somehow to cluster these lines together into a single object rather than treat them separately as you would for a non-eccentric system. So I think I have two more topics on searches. One is semi-coherent methods, and then the last time I talk a little bit about detecting backgrounds. So semi-coherent methods, these are some amalgam between the two previous techniques. Semi-coherent means that you do part of it coherently, i.e. with phase matching, so match filtering, and then the other part incoherently. Why would we ever want to do this? We know that match filtering is optimal. It is optimal, but you can't always do it because you need templates across your parameter space. And for certain types of source, like emeries, the parameter space is too big to realistically construct a template bank. This is also true for LIGO, for the pulsar searches. Pulsars, the parameter space is so big that if you're searching for signals that are present for years of LIGO data, you need too many templates, and you can't do fully coherent match filtering. And so what you can do instead is do match filtering for as long a section of waveform as you can handle. A few weeks, so it says 2 weeks here. That's when we looked at this, it was in 2002, where computers weren't as powerful as they are now. I think we could probably do at least 6 or 8 weeks for emeries these days. But the basic idea is the same. You can't do a fully coherent search for an emery, so you search for bits of the emery. You do match filtering on shorter waveform segments, and then an in-spiral that actually proceeds through your whole data will have a high overlap with different ones of these shorter templates at different times. And so there will then be tracks through this set of templates that you've used to overlap the data that will correspond to physical Emery trajectories. And so the idea of the search is you do this match filtering on each Emery, so on each short segment. That gives you an SNR squared in a segment, and then you add up these SNRs along the tracks that correspond to real physical Emery signals. And so it's the fact that you just add the SNRs at the second stage that makes it incoherent, because you're not forcing phase consistency from one segment to the next. Okay. So this process loses you sensitivity. You have to set your threshold for detection in terms of distance to about a factor of 2 closer if you do this than you would if you could do fully coherent match filtering. But it is a way that you can still do detection of difficult systems like Emery's, even when match filtering is not computationally tractable. So as I mentioned, the other area where this is used is LIGO searches for unknown pulsars, where you have to search over frequencies, frequency derivatives, sky positions, and so on, and the signals are very long. I mean, this is the main reason that we need these sorts of techniques for Emery's and also for unknown pulsars. The signal lasts the entire length of the data, which can be years. So you get very many cycles, and matching all of those cycles needs very many templates, and that's what makes match filtering impractical. So for LIGO, there are a couple of methods that are used. I think there may be more than 2 now, judging from the recent papers, but they all work in similar ways to what I just described. There's a stack slide algorithm which does what I just said. And then there's something called the Hough Transform search. The Hough Transform is a technique that was developed for in image analysis to detect simple shapes. So specifically for image analysis, you're looking for edges. In the case of these sorts of methods, we would be looking for tracks corresponding to inspirals. So how that's used is you first do this coherent matching on short segments of data. That gives you an output, which is your overlap in each of your templates at each time segment. And so you can put that on a grid, like this grid that I had here, and that then gives you something that is like an image, and you can search for edges, so tracks, in this image using the Hough Transform method. Okay, so these are powerful techniques, but they require a lot of computational power, and the way that LIGO has solved this problem is using distributed computing, in particular Einstein at home. So you may have heard of SETI at home before. This is basically one of those things where you can download some code onto your computer that is a screensaver, and so when you're not using your computer, it uses your idle CPU for hours to do science. Okay? And in the LIGO case, it's looking for pulsars in LIGO data, but also it's looked for pulsars in other datasets, so radio datasets and so on. So this was released in 2005, originally to coincide with the World Year of Physics. Computers analyze different sections of data, and at the moment there are about 500,000 active users of Einstein at home, and their average computing power is 5 gigaflops. So that's 5 billion floating point operations per second overall. So it's accumulated a pretty sizable cluster just by doing this. Now, Einstein at home has not discovered any gravitational waves, but they have made a number of significant discoveries when analysing other datasets. So they've found a number of pulsars in radio data that were not otherwise known using this method. Okay, so the last topic before coffee break, I'm going to say a little bit about searching for backgrounds. So I've said a bit about searching for using match filtering. Match filtering relies on having a template for the data, the template for your signal that you're looking for. You don't have that in the case of a background. And then you have these excess power searches, which are looking for things that for which you don't have templates, but you are looking for things that are concentrated somehow in time and frequency. So you're looking for tracks of excess power. A background is neither of those cases. You don't have a model, it's a stochastic thing, so you can't predict the amplitude as a function of frequency or the phase. But it's also distributed, so it's something that is present across many frequencies and over many times. And so that makes this a bit more challenging than those other the other cases. Okay. So the primary way that you can hope to find a background is by having more than one detector and looking for things that are common between your detectors. So it's a bit similar to Bayes' way of looking for these common wavelets. You're looking for a noise source that is common to both detectors, and then you assume that that can't be terrestrial, because if it was, then it's somehow operating at large distances, and so more likely it's of astrophysical origin. So I'll comment here that C and B polarization is a probe of backgrounds. I haven't really talked about detecting gravitational waves using C and B, so I won't say anything more about it. In the case of using interferometers, what we do is take data from one detector and cross-correlate it with data from the other. So it's like taking the dot product of one detector data stream with another, but as usual we do things slightly differently by introducing a filter, so we don't necessarily line these two data sets up in time. So our cross-correlation statistic is typically the integral of h1 of t, so that's the data coming out of one detector, times this kernel function, times the data coming out of the other detector, which you can write in as a Fourier integral in the usual way. This convolution becomes a product of Fourier transforms. So your cross-correlation is basically taking the Fourier domain product of your data sets weighted by the Fourier transform of your kernel. Now you can ask, what is the expected value of this cross-correlation for different choices of your filter. That's like your signal, your estimate of the size of your signal. And then you can attempt to choose that kernel such that you maximize that signal to noise. So this is exactly the same as the derivation of the optimal filter. We have signal, which is the expectation value of this thing when you have only astrophysical sources of H, and you compare that to the RMS value of the output when you only have noise contributions. Okay, now what you find is that your expected value of this cross-correlation depends on how particular signals manifest themselves in your two detectors. So it's not just the power. I mean, you take an expectation value of this, it looks kind of like Q and the expectation of H1 and H2. That is what you get, but H1 and H2, if your detectors are not exactly the same place, they have slightly different responses to sources coming from different directions, and that's characterized by something called the overlap reduction function. So you end up with an expectation value for this cross-correlation signal that is an integral over frequency of your filter times the power in the background times this overlap reduction function. Now, if you then try and maximize this, you find that your optimal filter is proportional to your overlap reduction function times the power in the background divided by the product of the noise, powers in your two detectors. So this basically means you place more weight on the detector with lower noise in taking the overlap, and you also account for the fact through this gamma that your detectors are differentially sensitive to components of the background. Okay, so if you ever read papers about stochastic backgrounds, they will talk about this overlap reduction function. The point is that if this is close to 1, then you're getting most of the gradation wave power. If it's close to 0, then you don't have much signal, and so you're going to be able to tell very easily whether there's a background there or not. Now for LIGO, these are what the overlap reduction functions look like. These are overlap reduction functions between the Livingston detector and various other detectors. In particular, so the green one that looks good because it's close to 1 over a wide range of frequencies. This was Allegro, which was a bar detector that was also in Louisiana. So this is very close to being 1 because it was almost at the same site. And so that's why it responds in the same way to gravitational waves. The purple line here, which is this one, is the overlap reduction function when you did a cross correlation between LIGO detector in Livingston and LIGO detector in Hanford. And this is only close to 1 at low frequency. By the time you get to 100 Hz, you've essentially lost sensitivity. So this tells us that we cannot, essentially at higher frequencies, the reason for this is that the detectors are sufficiently far apart that you're many gravitational wavelengths away. So there's no correlation between the signal in your two detectors. Okay, so LIGO cross-correlation searches are only sensitive to very low frequency components of the background, below a few tens of hertz, and that is it's a fact of life, unfortunately, but it is what it is. For pulsar timing, the primary source that we're looking for is this background generated by supermassive black holes that I mentioned earlier. And for pulsar timing, your different detectors are different pulsars. So you can also do this same argument. You can say, well, I'm looking for the background. To find that background, I'm going to take my signal from one pulsar, which is the measurement of the timing, so the difference between the time of arrival of a pulse and the predicted time of arrival of that pulse. And I'm going to take this other pulsar over here and measure the same thing, and I'm going to cross-correlate those. Now, the analysis is then the same, and you can calculate an overlap reduction function, and what you get is something that's referred to as the Hellings and Downs curve, because they first calculate it, and it looks like this. It's a function only of the angular separation of the pulsars on the sky, but it's something that is varies between 1 and around minus 0.3 as you change the angular separation. Okay, now, this looks much better for doing these kinds of analyses because you have much stronger correlations between all of the pulsars in your array than you do for the LIGO case, and that's basically just the wavelength difference. Now, another thing the overlap reduction function tells you is basically, so the overlap reduction function is telling you the size of the correlated signal you expect to see. And it's something that is characteristic of the model of the background that you use. So this is assuming that the background is isotropic, and which means it's isotropic. If you make other assumptions about the background, you get slightly different correlation curves. And so if you go out and measure the background, you might expect to be able to tell the difference between different parts of the background. So in this case, what we've done is simulate a background that is not completely isotropic, but it has an anisotropic power distribution determined by a quadrupole moment. The effect of that is to scatter the cross correlations in a predictable way about the relative value. And so if you go and take these measurements, and you can measure things accurately enough, then you can hope to distinguish between basically the anisotropies in the background by looking at these cross-correlation signatures. Yeah, and these are, again, similar list of these are the difference in the Hamilton Downs like curves for different orders of multiple perturbations of the background. So the black is the standard Hamilton Downs case, and then these others are more optical and hexadecadal background. Okay. This probably should have been in the talk this morning rather than this afternoon, but I'll mention it now and then we'll break for coffee. As I mentioned, the best type of cross-correlation search you could do is this one that was between LIGO and Allegro, the bar detector, also in Louisiana. Allegro is no longer operating, so this search can't be done anymore, but the best result that was obtained from this cross-correlation was a 90% confidence limit on omega 0.5, which is much larger than we might expect it to be, at a frequency of about 900 Hz. There are other limits that LIGO has subsequently placed on stochastic backgrounds using cross-correlations between the two LIGO instruments, which have now beaten this. So in the earlier talk, it's here because of the to illustrate that even though we had a good overlap reduction function in this case, the constraint is not very great, and that's because Allegro is not very sensitive relative to LIGO. So even if you have a large overlap reduction function, it doesn't mean you're particularly sensitive, because if the noise in one of the detectors is much bigger than the other, then that wipes out all of the signal. Okay, so the final thing to talk about is other types of backgrounds you might have to look for. So the alternatives are called popcorn noise and periodic noise. So popcorn noise is something that lies between individually resolvable sources and background. So we've got a background that's being generated by a large number of events. If some of those events will be close enough to be individually resolved, others will be farther away, and so you won't see them. If the density of those sources is high, you get a background. If it's very low, you can resolve them all individually. Somewhere in between, you have popcorn noise, so some of them are too close together to be distinguished, and others are far enough apart that they can't be. So you can talk about popcorn noise, that's what they mean. And then periodic noise, this is if you have a background that has a time dependence in it. It sounds a bit odd, but it's something we expect for LISA, because the LISA background is dominated by these white wall binaries that are in the galactic plane, and at parts of the year LISA will be more sensitive to gravitational waves coming from that direction than it will be at other times of the year. And so we have this background in the data, but this background will go up and down as LISA will return to the sun in a predictable way, but it means the background properties are a bit different than you might always assume. The analysis techniques are the same in both of these cases. You can still want to look for these things with cross-correlation, but you get slight differences in the optimal filter, because that optimal filter folds in the fact, in this case, that the noise is popcorn-like, and in this case, the background is going up and down. So the actual statistic is a bit different, but the basic principle is that you're looking for something that's happening in both of your detectors at the same time is essentially the same. Okay, so we'll take a break for coffee. I assume it's outside.